We're still doing this remotely, so let's just start straight away. Hopefully you've got whiteboards. So on your whiteboards, can you draw for me an atom? Can you label all the parts of the atom that you know? And then once you've done that, can you just kind of fill in the missing parts from that table below? It just says name of 3 subatomic particles, the relative mass and the relative charge. I've done the top line for you. So draw an atom, label all the parts of that atom that you have drawn, and then fill in the table below with as much information as you can. I will stop. Hopefully your teacher will pause and allow you to just finish. Go. Do it. Go. Okay, so let's just check the answers to that. Hopefully your diagram would have looked something like this, but it's not moving. Come on. There we go. You would have had here is a nice and simple atom. Get my little pen going. We have in the nucleus we have protons and neutrons. You hopefully labelled that nucleus as well. And then around the outside we have electrons. Protons, neutrons in the nucleus, and around the outside are the electrons. And filling in the table, you should have noticed, hopefully, that the neutron has the same relative mass as the proton, whereas the electron has very small. Some things say almost 0, other things say about 1/2000th. Basically, a proton is 2,000 times larger and heavier than an electron, so it's so small. If you have 2,000 electrons, it's only the same as 1 proton. So they're so small, we can almost ignore their mass. The charge of a proton is +1, proton positive. Charge of a neutron is neutral, no charge. And charge of an electron is negative, -1. Hopefully you got those. They're important parts of what we're doing today. Another quick review. We're doing everything on the periodic table. I'm just making sure that you remember what these numbers on the periodic table mean. So first of all, your periodic table has 2 numbers in it. It has a big number and a small number. The one in your planner and the one you get in the exam are slightly different. I think they have the numbers the other way round. But the bigger number is the mass number. It tells us the number of protons and neutrons inside our atom. If I go back to here, this element here, the mass number would just be how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be 12. So the mass number is the total number of particles inside the nucleus. 23 for the sodium one. And the smaller number is the atomic number, and that tells us how many of them are protons. The atomic number, the number of protons in an atom. It's its atomic number. Every atom of an element has the same number of protons. So if it has 11 protons, for example, it's sodium. If it has 3 protons, it's lithium. If it has 1 proton, it's hydrogen. The proton basically tells you what the element is. Different elements have different number of protons, and every atom should have the same number of protons as the number of electrons. So here we go. The mass number of an atom is the total number of protons and neutrons. So the number of protons is the atomic number. Smaller number here, 11, that's number of protons. The number of electrons is exactly the same. 11, the atomic number is 11, and the number of neutrons is the big number minus the small number. The number of protons and neutrons minus the number of protons tells you the atomic number. Relatively simple. Right, let's see if you can work that out. So, here we have 2 elements, lithium and beryllium. Can you, using the information there on those 2 things, tell me how many protons lithium has, how many protons beryllium has, how many electrons do they have, and how many neutrons? I'll just give you a minute, pause the video, and answer the question. Write it on your whiteboards. Pause and write it on your whiteboards. Are you done? Let's check your answers. So for lithium, the 3 means it has 3 protons. The 3 also means it has 3 electrons. And then to do the maths, 7, the big number, minus 3 tells us we have 4 neutrons. If you go to the other one, beryllium, 4 protons. The number 4 tells us 4 protons, which means it also has 4 electrons. And 9 minus 4 equals 5. Quick maths. 5 neutrons. Okay, so this is the periodic table. This is what we're mostly focusing on today. And the periodic table looks like this, because one dude called Dmitry Mendeleev, actually, he used other people's work too, but he made it the way it is. So we're going to focus on why it looks like that. This is the one you're going to be given in the exam. So you need to know this one. It doesn't have those extra bits at the bottom. The numbering's slightly different to the one in your planners. It's also no colours. So this is the one you're going to use in the exam. So this is the one I'm going to show you. Okay, so first of all, when Dmitry Mendeleev and the people before him were making the periodic table, they didn't know about protons, they didn't know about neutrons, and they didn't know about electrons. They hadn't been discovered. So what they did was they tried to order them by something called their atomic weight. The atomic weight is similar to the atomic mass, but it's not as detailed. So they just put them together based upon what they thought was the atomic mass, and they ordered them in the atomic mass. But before Mendeleev, they just put them in order of atomic mass, and if they were like things they didn't know about, they just put them in an order. They were also grouped with randomly. Dmitry Mendeleev, the dude, he did something very clever. He arranged them in order of their atomic weights, but he also took them in to account of the properties and their compounds. Basically, he left gaps because he saw that if you go up in atomic weight of 1, 2, 3, 4, if there was number 7 missing, instead of thinking, oh, 7 doesn't exist, he says, 7 exists, they just haven't found it yet. So they left a gap for it. He also, not only did he leave gaps for them, he was able to predict what that missing element was like based upon the other elements around it. So he actually did that for a couple of elements. He also lined them up with particular properties in groups. So, for example, this is what it's looked like now. This is the modern periodic table. In the modern periodic table, here's a little note, my head's in the way, but basically, we have rows. Rows are called periods in the periodic table. Here we have number on the side, period number 1, 2, 3, 4, 5. So, top row is period 1. The second row is period 2. The third row is period 3. And we go across in increasing atomic number. Number 1, number 2, number 3, number 4, 5, 6, 7, and going on. He also grouped them in groups, which means like a column vertically. They are things that are similar. They behave in a similar way. Every element in group 1 behaves in a similar manner. Every element in group 2 behaves in a similar manner. 7 in a similar manner. So vertically, they are called groups. It's not moving on. Give me a second. So here we go. Here's an example. Everything in group 1, we're going to look at those more later, are soft metals, and they explode if you put them in water. Everything in the middle are transition metals. They behave like normal metals. They're good conductors, high density. Everything in group 7, very reactive, toxic, and they all smell like chlorine, including fluorine. And in group 0, my head is in the way, but they don't. They're all gases, and they don't react with anything. We'll go over those in more detail. Right, time for questions. 7 questions. Can you answer these questions on your whiteboard? The answers will come up in a minute. What are the rows on a periodic table called? What are the columns on a periodic table called? Why did Mendeleev leave gaps in his periodic table? How could he predict the properties of these elements? Why didn't he arrange them in order of atomic mass? What did he arrange them in order of, and why is it an unusual shape? Pause. Answer the questions. I'll come back, I'll give you the answers in just a moment. Hopefully you're done. Let's give you the answers. The rows on the periodic table are called periods. The columns on the periodic table are called groups. Why did he leave gaps? Elements that had not been discovered, but he predicted that they would exist. How could he predict the properties? He compared them to the known elements either side of them in the periodic table. Why didn't he... Oh, that's not animated very well. Why didn't he arrange them in order of atomic mass? They didn't know about atomic mass. They didn't know about protons, electrons, or neutrons. So how did he arrange them? He arranged them in atomic weight. And why did he do it in unusual shape? The unusual shape was so he could group elements with similar properties together. That's why you have some groups that are really tall and some that are not so tall. Right. Important part about the periodic table is electrons and how the electrons are structured. So electrons exist in shells. If you start adding electrons to an atom, you have to fill from the first shell. The first shell is small. It can only hold 2 electrons. The second shell is bigger. It can hold up to 8 electrons. The third shell is big as well. It can also hold 8 electrons. The link between the electrons, the shells and the periodic table is, if you look down here, where's the mouse gone? There it is. No? Okay. The number of shells is the same as the period number. If you are in period number 2, your atom will have 2 shells. If you're in period number 1, your atom will have 1 shell. If you're in period number 3, your atom will have 3 shells. The group number tells you how many you have in the outer shell. If you're in group 1, you have 1 electron in the outer shell. Group number 2 has 2 electrons in the outer shell. And group number 3 has 3 electrons in the outer shell. The atomic number is how many electrons it has altogether. When we can write them, so maybe you want to write that down, it's up to you. You can do that. When you write about the electronic structure, you can do it in this way. So first example, this is just review. You either write it in numbers. So for example, this is sodium. Sodium has 11, an atomic number of 11. So it has 11 protons and 11 electrons. So 2 electrons in the first shell. Here we have them 2. Then the second one has 8. 2 plus 8, that's 10. That means there's 1 left for the outer shell. So you can either write it as 2, 8, 1. So the comma tells you the different shells. Or you can just draw it like this. 2 on the inner shell, 8 on the next shell, 1 on the last shell. You either draw your electrons as a dot or a cross. Going back to how they're arranged in the periodic table, we talked about this before. Group 1, soft metals that explode in water. Group 7, metals that toxic, smell like chlorine. And group 0 don't react with anything. Everything in group 1 has 1 electron in the outer shell. Everything in group 7 has 7 electrons in the outer shell. Everything in group 6 has 6 electrons in the outer shell. Basically, where you are in the periodic table tells you, 1, what it's going to be like, and 2, how many electrons it has in the outer shell. And those 2 things are linked. Okay, so let's see if you know what I'm talking about. Using the periodic table, can you write for me the electron arrangement for lithium? So do it in brackets, the numbers in brackets. Aluminium, carbon. And then for the other 2, trickier, can you draw the electron arrangement for fluorine and for hydrogen? Pause and do these questions on your whiteboard. Okay, right. First one, lithium. You can see lithium is in group 2. No, it's not. It's in group 1. It's in row 2, period 2. So it has 2 shells. And it's in group 1. So the outer shell must be 1. So the electron arrangement for lithium is 2, 1. Aluminium. There's my little mouse. Mouse is not working. Aluminium is in period 3. And group 3, period 3, group 3. So it has 3 shells, so we need 3 numbers, and the last one has to be 3. So it goes 2, 8, 3. Carbon is in period 2, and it is group number 4. So its last number has to be 4, and they have to have 2 numbers, so 2, 4. Drawing the electron arrangement for fluorine. Fluorine is also in period 2, so you have to draw 2 shells. It's in group 7, so the outer shell has to have 7. So fluorine, inner shell has 2, the outer shell has 7. And hydrogen easiest of all, but is in group 1 and period 1, so it has one shell with one electron. Easy. Okay, another way the periodic table is arranged is with metals and non-metals. On the left-hand side, most of them are metals actually. The left-hand side, and all in red here, are metals. The other ones in yellow are non-metals. I think this is probably the easiest question. All of these are properties of metals, properties of non-metals. So we've got things like poor conductor of electricity, high density, ductile, brittle, dull, poor conductor of heat. My head's in the way there. Good conductor of electricity, malleable, shiny, low density, good conductor of heat. This will make a good flashcard. What are the properties of metals? If you put that little table down, can you put the correct properties in the correct category? So all of those things that are scattered around the periodic table either go in property of a metal or property of a non-metal. For example, I'll give you one to start with. Metals are good conductors of electricity. So that will be the first one you put in perhaps the top property of a metal. And if they're good conductors of electricity, then the other side, non-metal, would be a poor conductor of electricity. So I've given you the first one of each. Pause, either do it on a whiteboard or do it on a flashcard, and unpause when you're ready, and I will give you the answers. Okay, let's see. Did you have this? So properties of a metal are good conductor of heat. I mentioned that already. No, good conductor of electricity. Good conductor of heat. Metals are shiny. Metals have a high density, which means if you hold some metal in your hand, it feels heavy for its size. Metals are malleable, means you can change their shape with a hammer. And ductile means you can kind of, like if you have enough force, you can pull on either side and draw it out. Non-metals are generally the opposite. They are poor conductors of electricity. They are poor conductors of heat. They are not shiny. They are dull, as in not very shiny, not as in boring. They have a low density. If you hold a piece of metal and a non-metal, the same size, the metal will be much heavier. Brittle means it needs to break, and I put brittle again. Don't know why. Did I miss one? No, just put brittle twice. Check me out. Okay, so now we've gone over the general setup of the periodic table. Now we need to look at group 0, group 1 and group 7. So first of all, group 0. They are on the far right hand side of the periodic table. They are called the noble gases, and the noble gases all have very low boiling points. Again, my head's in the way to cover the word points. But the boiling points do increase as you go down the table. In fact, helium at the top has the lowest possible boiling point. It's like minus 273. And then as we go along, the boiling points do get higher, but still really low. Like xenon, still below minus 100 degrees. As you go down the periodic table, the atoms become bigger because they have more shells. And they have more protons and neutrons. So the atoms get bigger, and so therefore the forces between the atoms get stronger, and then it's harder to melt them or boil them. So the energy needed to overcome increases. The thing with noble gases is they are very unreactive. They don't take part in a chemical reaction. Helium, neon, argon, krypton, xenon, they just don't care. You put them in a chemical reaction, they do nothing. And the reason why is they all have a full outer shell. Basically, elements react to get a full outer shell. They do something to either lose electrons or gain electrons to have a full outer shell. These ones already have a full outer shell, so they don't need to do anything. So they never bother reacting. If you want to take a note, I'll just pause for a moment, or your teacher can. Okay. Group 1 elements are very different to the group 0 elements. They are called alkali metals. They are a metal, and they are on the metal side of the periodic table, but they are unusual metals because they are soft. You can cut them with a knife, like just a normal sharp knife, or a not very sharp knife, depending on they are. They can just be chopped with a knife. They have very low melting points. Some of them melt at room temperatures, and they have low density. Lithium and sodium and potassium, if you put them on water, actually float. Normal metals don't float on water as a lump. These ones will float when they're on water. These are the ones that if you put them in water, they catch fire. As you put them in water, they catch fire. As you go down the periodic table, they get more and more violent reaction. Lithium fizzes, pops. Sodium catches fire, pops. Potassium explodes. Rubidium explodes before it even touches the water. They're crazy reactions. Excuse me. And they go down the table, they get more violent. That is because they all have one in their outer shell. They want to lose one electron. If you are something like lithium, see lithium here on the left hand side, lithium's one electron on the outer shell is really close to the nucleus. So it's really hard for that one negative electron to escape from the positive nucleus. But if you go over to potassium, that one electron is further away from the nucleus. So it's easier for that negative electron to escape the positive nucleus. So there you go. They all want to lose an electron. It's easier to lose an electron if you are bigger. The negative electron isn't attracted to the positive nucleus if it is far away. Right, the last part of this is the group 7 elements. These are non-metals. They are on the right-hand side. Group 7. They're often called the halogens. They are simple molecules. They always exist as a pair when they're by themselves. So fluorine is F2, chlorine is Cl2, bromine is Br2. As they go down the periodic table, their melting point and boiling point also increase. Fluorine boils at 200 degrees, whereas chlorine 50, chlorine minus 50, bromine plus 50. So as they go down, again, because they are bigger, as you go down the periodic table, more energy is needed to overcome these forces. So as you go down the periodic table, they get bigger, so their boiling points go up and their melting points go up. Now these are opposite to the alkali metals. The most reactive one is at the top, and as you go down, they get less and less reactive. They are more reactive at the top. And this is because, if you look at them, they all have 7 electrons in their outer shell. There's 7 electrons in their outer shell. How many do they want to have a full outer shell? They want 8. So fluorine, it's very easy for fluorine to react and steal an electron because that outer shell is close to the nucleus. The positive nucleus can easily attract a negative electron. Chlorine, the next shell is a bit further away, so it's not as easy for the negative electron to be attracted to the positive shell. Bromine, even bigger, so it's harder for the positive nucleus to attract the negative electron. Iodine, even further, so they get less reactive as they get bigger. They want to gain an electron, but it's much harder to gain an electron when the shell is far away from the nucleus. Excuse me. Don't worry, you can't spread COVID via a video on YouTube. It just doesn't happen. Okay. Anyone notes? Anyone? Right, last part. There are probably other bits, but this is what I think is probably doable within a lesson. I think about reactions of these group 1 and group 7. Group 1 form +1 ions. They lose their electron, they become positive. They've lost a negative, they become positive. Group 7 form negative ions. They've got one space for an electron. They bring that extra electron in. Too many electrons, they're now negative. So group 1 and group 7 love to come together. Group 1, explosive, explode when they touch water. Group 7, poisonous, toxic. Bring them together, they make a salt. Nice and simple. So lithium plus fluorine minus make lithium fluoride, salt. Sodium plus chlorine minus, bring them together, sodium chloride. Easy. Okay, we can't finish without doing a few more questions. What happens to the reactivity of group 1 as you go down the periodic table? What happens to the reactivity of group 7 as you go down the periodic table? Why do group 0 not react? And why are group 7 and group 1 very reactive? I'll give you the answers in just a moment. So either pause the video and have a go, or I don't, but you should. Okay? Here are the answers. What happens to the reactivity of group 1 metals as you go down the periodic table? Group 1 get more reactive as you go down. What happens to group 7 as you go down? They get less reactive as you go down the periodic table. Why do group 0 not react? They don't react because they have a full outer shell and they don't need to react. Why are group 7 and group 1 very active? They are one electron away from a full outer shell. Group 1 has 1, they just need to lose 1. That's easy. And group 7 have 7, they need to gain 1. So the closer you are to having a full outer shell, the more reactive you are. Unless you have a full outer shell, then you just don't bother. Okay, lots of information there. Hopefully you got some good flashcards and you answered some questions. Love you. Bye.